Okay, so now we know how to set up our hypotheses. So now we want to talk about kind of the types of errors they call these inference errors that can be made, and also kind of our logic that we're going to go through. And this is kind of an introduction, and then we'll start actually doing some hypothesis tests. So we basically start off assuming that the null hypothesis is true. And then we look at the evidence that's provided by the sample, and then we find out whether those samples give us enough evidence to reject the null hypothesis. If there is sufficient evidence to reject the null hypothesis, then we conclude that the alternative hypothesis is likely to be true. However, keep in mind that we can't actually prove that the alternative hypothesis is likely to be true. We can't be 100% certain, but it turns out we can sort of quantify our level of certainty by using a confidence interval or a confidence level, similar to what we did with confidence intervals. And there is indeed a relationship between the confidence interval and the related hypothesis test. If there is not sufficient evidence to reject the null hypothesis, then we basically just hold on to our assumption that the null hypothesis is true. But again, we still haven't proved it. We haven't confirmed. We're not 100% certain that that null hypothesis is true about the population, because we can't access the population. All we conclude is that whatever this particular sample is didn't give us enough evidence to reject the null hypothesis. So basically, one of these two things is going to happen. We're going to reject the null hypothesis, H0, or we're going to fail to reject the null hypothesis, H0. Notice, we never accept the null hypothesis, because that would mean like we were proving something about the population, which we cannot do without accessing the population. Okay? Okay, so those are the two things that we can come up with here. All right. So now we're going to look at what we call inference errors. Okay, even if we do anything right, we can still make what we call an inference error. So in statistics, I almost never tell anybody they made an error. I usually tell them if they made a mistake, because error is used in a very specific way in statistics. And it means, for example, it can mean the deviation from the mean. In this case, it may be an inference error, which can happen to any researcher even if they do everything correctly. In other words, they didn't make any mistakes. They could still make an inference error because of characteristics of their particular sample. Okay, so we also talk about rounding error, which is basically error that creeps in from rounding your decimals. Even if you round them correctly, you still get rounding error. Okay, and so a rounding mistake is what you actually round your decimals wrong. Rounding error is what creeps in when you round them correctly, but you still lose a little bit of information when you round the number. Okay, so basically what's going to happen is that we have some unknown population. Okay, and let's just, for the sake of simplicity, let's assume that our H0 is about a population mean. So we have this unknown population. We have a benchmark. So if H0, if the population mean is really equal to the benchmark, well, maybe that's really true. Or maybe it's not. If we actually had access to the population, we could know whether it was true or not, but we don't. Okay, so but one or the other of those things has got to be true. So then we're going to put that with the results of our hypothesis test. Okay, so let's do a little, let's put a couple of symbols here. Okay, so alpha. So our alpha is the conditional probability that the H0 is rejected given that H0 is true. Okay, Okay, so conditional means that a certain thing is given. So in this case, the alpha is the probability that the H0 is rejected if the H0 is indeed true. Okay, and then our other one is beta. Again, we've got our Greek letters going here. This is the conditional probability that H0 is not rejected, given that, there's my given for the conditional again, that my H0 is false. Okay, and so basically, here's our key. So H0 is true, but it's rejected. Beta is the conditional probability that if H0 is false, then the H0 is not rejected. Okay, so where do these go in this chart? Okay, so let's look at this chart. So let's suppose H0 is really true. Okay, so hopefully what would happen is if we get a sample that ends up containing the right information, then we could conclude that we don't end up rejecting H0, and then that would end up being correct, right? So that's what we call a correct inference. Or what else could happen if H0 is true? We could end up rejecting it anyway. Okay, and the probability that this happens is alpha. Okay, and this alpha is a conditional probability. Remember, this alpha only applies if the H0 is true. If H0 is false, alpha has nothing to do with anything. Okay, so if we're given that H0 is true, and the probability of rejecting it anyway is alpha, then what's the probability of not rejecting it? 1 minus alpha, because remember, those are the only two options, and they have to add up to 1. Okay, if we end up rejecting H0 when it's true, we call that a type 1 error. Okay, that is a type 1 error. All right, now let's talk about what happens if H0 is false. And by the way, that immediately puts us over onto H1 is true. Our alternative hypothesis is true. So if H0 is false, then the correct inference would be to reject H0. The incorrect inference, the wrong inference, would be to fail to reject H0. And it turns out that that probability is our conditional probability beta. Okay, and that type of error is called a type 2 error. So the first type of error, which is rejecting H0 when H0 is true, we call that a type 1 error. And the other type of error, if H0 is false but we end up not rejecting it, we call that a type 2 error. Okay, and then in that case, if H0 is indeed false, then the probability of a correct inference would end up being 1 minus beta. Okay, so in any hypothesis test, any of these can happen. Okay, so sometimes this situation here, and I don't think it's the greatest example, but you'll see it a lot. Sometimes this would be basically kind of a courtroom analogy is done to where we're trying to assess whether a jury's trying to assess evidence and decide whether someone is guilty or not. And so if the person is really innocent and you end up convicting them anyway, so basically you call the conviction like the rejection. And so in this case, we reject H0, we convict the man when we shouldn't have. Okay, and then the other type of, and sometimes this is also called a false positive. Again, I don't think that's a super descriptive term, but you may see it somewhere. Okay, and then the other situation over here would be if you release a guilty person. And sometimes this is called a false negative. So we missed the person's guilt. Where over here on this one we found guilt where there wasn't any, but on this one we failed to find the guilt that there was. So sometimes you'll see that. I think a better analogy, if you've ever heard the story about the boy who cried wolf, so basically the boy cries wolf and says a wolf is coming, and all the townspeople hide, and that happens I think usually a couple of times, and then there was no wolf, and then later on there is a wolf and he cries wolf and nobody believes him because of what happened the first time. So basically what happens here in the type 1 error, and if you know the story you can remember the type 1 and type 2 by knowing which one comes first in the story. So basically what happens here is that people believe there is a wolf, and I'm going to put the word effect here in parentheses. Okay, so people believe there is a wolf when there is not. Okay, why did I put the word effect in parentheses? Because with statistics, we're basically usually trying to figure out whether there's an effect or a interesting difference between two things. So for example, with a potato chip example, if we are testing whether, if we were doing a hypothesis test and we're trying to figure out if the sizes of the potato chips are really 8 ounces, well, where would they be an interesting difference? If somehow, golly, our sample provided evidence that the mean was not 8 ounces. Okay, so we can think of that difference as being the wolf or the effect or the interesting difference. If you were doing a hypothesis test about the effectiveness between two different cancer treatments, what you'd be looking for is, like, if they all turned out to be the same, we didn't find a wolf, we didn't find an effect. But if we do find, ooh, treatment A is better, we call that an effect, which represents some kind of an interesting difference. Or you can think of it as a wolf if you like the wolf story. Okay, and so then the type 2 error, this would be when people do not believe there is a wolf, but there is one. Okay, and so that happens when, in that case, maybe if you're, maybe the manufacturer, if we're trying to test whether all the potato chips, whether their population mean is 8 ounces. So maybe the population mean is really like 6 ounces, but we happen to get a bunch of big bags in our sample, and almost all our samples were close to 8 ounces, all the bags in our sample. And so we ended up concluding that everything was fine, that as far as we could tell, the population mean really is 8 ounces. So we missed it because we missed the wolf, we missed the effect because of the characteristics of our particular sample. Okay? So it could be that if you're doing 2 cancer drugs and maybe one of them really is better, but in this particular sample, the patients who took that drug just happened to be a group of patients who didn't react well to it. And so you end up not picking up on the fact that the drug is better. That can happen. And that can happen even if you do everything correctly. So basically the alpha ends up sort of controlling what level of risk of making a type 1 error. Because remember, the alpha is the conditional probability of rejecting H0 given that H0 is true. And this is what we call the level of significance, and you have to choose it in advance before you analyze the sample. Okay, and then common choices for alpha, and we've seen these before. 0.1, 0.05, 0.01. And so, like with the confidence intervals, if we had 0.1, then where does the 90% come from? Take 0.1, subtract from 1, you get 0.90, and then you convert that to a decimal, right? So those should look very familiar to you. Okay, let's see if we can describe type 1 and type 2 errors for a couple of situations. So let's suppose we have a vet who is trying to study whether wild Mustangs have a front hoof angle of 45 degrees, and 45 degrees is considered standard, most desirable for domestic horses. And so we want to figure out how a type 1 and type 2 error, what they would look like in this situation. So first of all, the things that we want to do is we want to write down our H0 and our H1, okay? And so my mu is going to be the population mean hoof angle for all the Mustangs. So that's the whole population of the Mustangs. Okay, and so what's our benchmark? Our benchmark is 45 degrees. So what are we going to put for our null hypothesis? Mu equals 45 degrees, right? And so now we need to write our alternative hypothesis. So that's mu, and we're going to have our 45 degrees there. We need to decide if it's going to be two-tailed or one-tailed. So we look here to see if the problem is steering us in a direction, whether they think the wild Mustangs is bigger or smaller than 45 degrees. It does not seem to be steering us in a direction. So we are just going to say 45 degrees. Okay, now we want to look at the type 1 and the type 2 errors. So our type 1 error. Okay, remember this is when we expect a wolf when there isn't one, or an effect, right? So what this would mean is that we conclude that the Mustang's hooves differ from 45 degrees. When really they are 45 degrees. Or at least their mean for all of them is 45 degrees. Okay? So what this means is that we found an effect or an interesting difference that doesn't really exist. Or a wolf that doesn't really exist. Okay, so that would be our type 1 error. Okay, so our type 2 error, remember it's the second thing that happened in the wolf story. And so this is when there really is a wolf, but we don't think there is one. Okay, so what this means is that there really is an effect or an interesting difference, but we don't find it. So here, the Mustang's hooves differ from 45 degrees. We don't pick up on that difference in our sample. In other words, there is is an effect or an interesting difference or a wolf, but we missed it. Not because we did anything wrong, but just because of the characteristics of our particular sample. Okay? All right, let's do another one. Okay, we have a fact, which is that in the student body of Lone Star College North Harris, whatever particular time I looked this up, it was 61% women and 39% men. And let's say an administrator wants to find out whether the percentage of women in evening classes is also 61%. Okay, so let's write our null and alternative hypotheses and figure out what would happen in these various kinds of errors. Okay, so we want H0 and H1. Now this is a little bit different hypothesis test than what we have seen before. And so because we're basically, you can see that that 61% is our benchmark, right? And so we're going to call that P, and we'll talk more about this in a later section. This is going to be the proportion of women in the population. So this is for the whole population. Of what particular population? Of evening students at this campus. Okay, and we call that with a lowercase p. And so what our H0 and our H1 then are going to involve this lowercase p. Okay, and so for p, so what's my comparison here? Remember my benchmark proportion is, our proportion will be 0.61, and this is from the 61% is where that comes from. Okay, so we're going to put our 0.61 here. And then for my null hypothesis, I need to decide whether I'm getting a one-tailed test or a two-tailed test. So I look to see if the problem is steering me in a direction. Is it asking me, are the percentage of women higher or lower than 61%? Nope, it's just asking whether it's 61% or not. So this is going to be a two-tailed test again. Okay, so now we want to write down our type 1 and our type 2 errors. Sorry. Oops, sorry for all the scrolling. Let me try again. There we go. So my type 1 error. So remember what this means is we think there's a difference, but there's not. So basically we conclude that the percentage, or the proportion I should say, so this differs from 0.61 when really it doesn't. In other words, there's no difference on this one. Okay. So we found an interesting difference, but it was just a fluke of our sample. It really wasn't there. So we come to a wrong conclusion. So a type 2 error, okay, so remember this is when there really is a difference or an effect or a wolf, but we missed it. So here we would say the proportion of women differs from 0.61 but we end up not rejecting H0. In other words, so we don't pick up on this difference at all. So that's basically what's going on with our type 1 and our type 2 errors. And when we do hypothesis tests, unless we actually have access to the population, you're not going to know whether you made one of these. All you're going to be able to do is quantify probabilities that, for example, our alpha, remember our alpha, if our alpha is the conditional probability that H0 gets rejected even though it is true. So we will be able to state that using our alpha, and we're going to be able to sort of put limits on the probability that these things happen, but we can't avoid them for sure. Okay, I hope this helps you get started with hypothesis testing. See you next lesson.